Um, well, thanks for the EPA for inviting me here today. I'm going to be talking about something completely different, really. Bioaerosols. Okay, it actually only got mentioned once today by John Wenger. Thank you very much. And actually, bioaerosols, pollen and fungus spores, they've been around since the beginning, and they can be considered as a biopollutant. And actually, they're only going to become more important as time progresses. So I'm going to really talk today about how they're traditionally monitored, and maybe going towards real-time sensors to detect them, and maybe even using a bit of machine learning to forecast them into the future. So why do we care? Well, about 30% of people have an allergy to pollen or fungus spores. That's a huge part of the population that are truly affected. It affects their well-being, it affects their productivity. So it has huge impacts. I've already kind of alluded to it already, but climate affects these particles. Okay? The pollen season is extending, getting longer, and it's getting more intense. Actually, by about 2060, they reckon that allergy is going to double. So instead of having 30% of the population affected, we might have 60%. That'll be at epidemic levels. But of course, the most important cohort of people who I want to talk about are the people who have asthma. Okay, we have the fourth highest incidence of asthma in the world here in Ireland, about 400,000 people. And that's where it goes from a well-being problem to maybe a life and death problem. If they breathe in high concentrations of these particles, it can trigger an asthmatic attack, and it can have serious implications. So it costs us our time, our money, our sense of well-being. And if you want to put a cost in it, it's between 50 and 150 billion in Europe alone on allergy-related costs. So how do we monitor them? Well, the traditional method is kind of older, slower, but it's standardized, used all around Europe. And you can't get a more basic type of monitoring than this. It's just basically what we can see over here, kind of a pump that sucks in the ambient air onto a sticky substrate that kind of rotates at around 2 millimeters per minute. You bring that sticky substrate back to the lab, you stain it with a dye, and you actually literally count the pollen and fungus spores under a microscope. It takes forever to do. Laborious. Spent about 4 years of my PhD doing it. I never want to do it again. And you get a kind of slide like you have here. You count down it, and you get very nice information on the species, on the concentrations. And you get images like this, okay? And if you're a trained pollen or fungus spore identifier like I am, you can actually tell the differences between these. But I mentioned these are biopollutants, and they contribute to PM10. Pollen contributes to PM10, and fungus spores definitely contribute to PM2.5. So they can harm us, and they can infect us. And just to show you some of the pollen data for Ireland, we don't have much pollen data for Ireland. Okay, we've never had a national network. We don't really have a national forecast. And compared to other countries within Europe, which have 70, 60, 50 years of data, we lag far, far behind. But you can just see here, we have just a few time series plots here of total pollen. And if we just look for Dublin, for instance, it's kind of dominated by nettle pollen and grass pollen. Okay, and we normally think of grass pollen as the one that causes all of the allergy, but that's not true. I talked about climate change and how the season's getting longer and more intense. Well, I scraped together all of the amount of data that I could for pollen and fungus spores and just plotted it here. And if we look back into the 70s and 80s, well, the birch concentration was what we can see down here, on average about maybe 20 pollen grains per meter cubed on average and during the birch season. And as time has progressed, it's getting progressively larger, more intense. Birch is a significant allergen for Irish people, okay? So it has a huge effect on us. And it doesn't affect us during the summer, it affects us actually in the spring. So climate is affecting us. Increasing temperatures, increasing CO2 levels are lengthening the growth seasons, intensifying bioaerosols. This also happens for fungus spores as well. And just to show that, one of the work that I've been trying to do is trying to come up with a pollen calendar to show people that hay fever isn't just a summer ailment. It starts in January with alder and hazel. They're highly allergenic. And it'll end up, towards in September with nettle pollen, okay? If you add fungus spores into that hay fever season goes from January all the way to the end of October. So we're affected all the time by these. One of the interesting things that we did, okay, is that we looked at the phenological window for plants when they should be able to emit pollen. Okay, that's what that yellow trace is there. That's the phenological window for birch pollen and for alnus here, where we should expect the trees are able to release pollen. And as you'd expect, the highest concentrations are within that phenological window. Interestingly enough, though, if we look, there are a few peaks before that phenological window. So what's happening there? Is it medium to long-range transport episodes? Well, we've already heard today that air pollution doesn't respect boundaries. We think it is from a different place. If we look at these pollen types, we can see for those really high concentration days, actually the wind was coming from the UK. Okay, and there's far more ash trees in the UK. So this is one over here is just for ash, and this one here is for birch for those very high concentration days. And the wind, using this high split back trajectory model for air masses, was coming and shifting from the UK over to Ireland. So it's not just our locally produced trees here, it's transboundary. Moving now into the real time. So the one thing I wanted to talk about, why we wanted to even look at these in real time, well, the older methodologies, like I said, they're slower, they take ages, you go blind doing it. This could give you your information in real time. Okay, obviously, I can mention again the 50 to 150 billion for why we want to do these things, but interestingly, it can give you that high resolution information. A daily average, which is how it's generally done now, it mightn't go above, the symptoms for high-level allergy or maybe even less allergenic pollen, but we can see there's huge spikes during the day. Well, if we can monitor that, if we can model that, we can tell people, we can try and mitigate their exposure to these particles. Because, if you, breathe in a high concentration of birch pollen, even for a short period of time, you will start to get sensitized, okay? You will start to have an allergenic response if you're predisposed into that. So one of the instruments, I'll just talk a bit of some of the results. We did a funded campaign by the EPA, so thank you very much for that, for the POML project, sorry. And we used what's known as a WIBS. It's basically a particle counter, which counts every individual particle, gives you a size and a shape component for those individual particles, but also gives you kind of a fluorescence information on each of those individual particles. And it breaks it down into kind of 7 different categories, as you can see here by this kind of Venn diagram. If it's fluorescent, if it has certain fluorescence characteristics, we just call it an A particle, or a B particle, or a C particle. And if it has multiple of those, we just use an AB or ABC kind of classification. And having done some work with this instrument before, some of them are more linked to bioaerosols than others. A, ABC, BC tend to be linked with bioaerosols. But this instrument gives you the data instantaneously, not 2 weeks later, like the traditional monitor I mentioned earlier. So this is just straight to the point. We looked at nettle pollen and total pollen, and we saw that if we use BC particles, put a size filter on them as well for the size range of pollen, we actually got very good results. Okay, you can see over here the time series follows quite well. Just to look at the OR values here to see that the correlation does quite well. And we were able to get this data far quicker than we would using the traditional monitors. You can do it for fungal spores as well. Again, BC was useful for basidiospores. R-squareds aren't as good, but you kind of expect that for fungal spores, but decent enough. Again, wind's very important, not to be highlighted today by lots of people. Well, the wind for this campaign was southwest, as you might expect within Ireland. Okay, dominated there. You can see the high wind speeds from the southwest. But if we look at where actually nettle pollen was coming from, northwest, right over Phoenix Park. Interestingly enough, poaceae or grass pollen for this campaign, this more short, intense campaign, well, you saw a bit from kind of Phoenix Park as well, but actually more localized settings to our east. Okay, maybe Ivy Gardens for where our site was. So just kind of trying to use more advanced methodologies. Okay, we just basically used a classification from the WIBS, compared it to a pollen, compared it to a fungus spore. Can we get even better R-square values by using machine learning? Well, you can using multiple linear regression. If we just take, a BC particles, AC particles, actually a whole host of other ones that we can see here, we can actually get far better R-square values for fungal spores in this case. Okay, 0.77, that's pretty good, I think. And then why do we want to do this? Why do we collect this data? Well, we want to, forecast it. Okay, we want to mitigate people's exposure. And we created a whole host of models. The black trace here just indicates what we actually observe for birch pollen, and then we have like 4 or 5 different types of models, and they do okay. Okay, they're not too bad. But actually what we use, and to kind of use within weather prediction as well, if we use an ensemble method, if we take an average, a median, or a weighted mean of all of those models, it does far better. Okay, we can see the Spearman or coefficients there, up to about zero 0.8 when he's a weighted mean. And if we can predict this, if we can forecast this, okay, we can tell people when there's going to be high concentrations of these particles, they can take their antihistamine the day before. They won't be affected by the allergen as much. They can wear a mask. They can ask to work from home. All of these things to try and help people, save lives. Where do we need to go? Switzerland has 18 real-time monitoring sites for pollen. Okay, they've done a cost-benefit analysis, and they reckon it's a good way to go, and it'll pay for itself within a year. They don't use the WIBs like I just showed you. They use an even better version. Okay, again, it gives you those fluorescence information, gives you the size information, but it actually also gives you actual individual pictures of every particle that you see. Okay, so that's a massive amount of information. I think we should have our own network like that with one of these instruments here. Once we have that information, we can do the dispersion model, and we can help people mitigate their exposure. Thank you very much.